We have only spent one class looking at the limit definition of derivative, but I suspect that you're already tired of it. And I don't blame you. I mean, the limit definition of a derivative is fairly technical, and let's face it, if we had to compute derivatives, all derivatives by using that definition, probably would still be in the Middle Ages. But thank goodness, very quickly, very shortly after the basic concept of derivative was developed, people quickly figured out that there are some quick ways of computing derivatives that do not rely on the limit definition. And these are what we call differentiation rules. And that's what we're going to be looking at in the next set of videos. So first of all, let me clarify that a differentiation rule is a fast and efficient way to compute a derivative. It is not what the derivative is. You cannot use it as the definition of derivative, but you can certainly use it to speed up your computation of derivatives. Also, because of that, each one of these rules that we're going to see need to be proved. In other words, we have to show using somehow the definition, going back somehow to the limit definition of derivative, that the rule works. Otherwise, we're not allowed to use it. Okay, so for instance, even for something as simple as the constant rule, well, what is the constant rule? The constant rule says that if you have a function that is constant, its derivative is 0. Very quick, very fast, no limit to compute and so on. But why does that happen? Well, remember, what is the derivative? The derivative is supposed to be the slope of the curve, but if constant function the graph of a constant function is actually a horizontal line with therefore slope of 0. This is what it looks like. And if its slope is 0 at all points, its derivative is 0 at all points. So this may look like very simple and basic and so on, but we have to keep it in the back of our mind. This is not just a simple rule to allow us to get rid of constants, but it is a very important rule based on the definition itself. Here is another example, the linear rule. Okay, remember, with the derivative, we're looking for the slope of the tangent line. Well, what happens if our line is a function? Well, if our line is a function, the slope of the tangent line will be the slope of the line itself. And therefore, we can say that if we have a function of the form mx plus b, whatever m and b are, then its derivative is just m, the slope. Okay, so once again, why? Because the slope of such a line is m, and the derivative is in fact the slope. So if we're going to look at the graph of that line, it will look like that. The line itself is tangent to itself, and it's kind of a very simple basic situation, but we have to convince ourselves that that rule works. By the way, as an exercise, you may want to prove both the constant and the linear rules algebraically, that is, by using the definition. It's not that difficult, actually. It's a very easy application of the definition of derivative, and again, it will confirm that these rules in fact work. There's another very simple rule, that is the coefficient rule. And what does it say? Well, it says if your function is made up by multiplying a constant coefficient k times some function possibly involving x, then its derivative really depends only on the derivative of the part or the factor that contains x. The k just stays there, does absolutely nothing, and we can just carry it along. But again, this is a very simple rule. It basically tells us that coefficients as far as derivatives are concerned are dead baggage. We can just drag them along with us. But why does it work? Well, let's look at the proof of this particular rule by going back to the definition of derivative. Remember, the derivative is the limit as h approaches 0 of f of x plus h minus f of x over h, the big formula that I expect you to remember. What does it look like in this case? Our function is k times g of x. So that means in our case, f of x plus h becomes k times g of x plus h, and f of x becomes k times g of x. Well, there is a constant k. Or actually, I shouldn't say a constant, a common k, a common factor of k in the two terms. So we can pull that one out, and therefore the k can come out of the limit altogether. It does not depend on h. And what we're left with is just that limit, which is pretty much the same as that limit, except with a g instead of an f. And therefore, what that becomes is simply the derivative of g. So this is the basic idea. We can develop this fast formula, but we need to back them up with some proof, some solid argument to show that they are in fact correct.